the LZ78 or the tree structured impulsive algorithm. Right? So how does the LZ77 algorithm work? So in both algorithms, the first phrase is x1, the first symbol, and the LZ77 algorithm tries at each point to find the longest subsequence which has already been seen before. So that is going to be the next phrase. If the next symbol has not seen before, then that itself is the next phrase. But in general, it is the longest subsequence that has been seen previously. On the other hand, the LZ78 algorithm parses into phrases such that you look for the shortest subsequence which is not a previous phrase. Right? And we've seen that each of these are encoded into, so each phrase is encoded into either a pair or a triplet. In the LZ77 algorithm, it is encoded as, right. So in LZ77, the encoding is as follows. If there is no match previously, so if it's a new symbol, then you encode it as 0, comma, the new character. And if it's already a subsequence that has been seen previously, then it is 1 followed by the location and the length of the match. Right? So basically, you're storing certain bits and either a character in binary or certain positive integers. Similarly, in LZ78, the encoding is as follows. You always store the location of the previous phrase. So if there is a match, if there is a match, then you store the location. If there is no match, then you just store a 0. And then this is followed by the character. And this character you can represent, all of this has to be represented in binary. Okay. So we were saying that it is sometimes it's generally inefficient to represent these locations in using fixed length encoding, and therefore we discussed the variable length encoding of the positive integers, which is also prefix free. Right. So before we discuss that once again, any questions regarding the LZ77 and LZ78 algorithms? Yes, any questions? Okay, so our goal now is to design a prefix-free code for the set of positive integers. Now this has been studied for since a long time, and there are different encodings, each of which is optimal in certain scenarios. But this, I don't claim that the following scheme is optimal. You can, in fact, do slightly better than this, but it's good enough for our purposes. So the kind of scheme that I'm going to describe has the following guarantees. If you want to store or if you want to encode a positive integer m, then you can store this in a prefix-free fashion using just log m plus 2 log m plus 1 bits. All right. Okay. And how do we encode this? So if we just represent m as it is in binary, then it requires ceal of log m bits, right? And then, but we don't know what log m is, so the decoder doesn't know that it has to read precisely log m bits. So as a prefix, you store the binary representation of log m, right? And this requires log m bits, right? And then you store, but now you need to know what log m is, and therefore you store this in unary. Okay, so let's take an example, right? So suppose that I want to represent the integer 10 using this prefix free fashion. Okay, so I want to represent the number 10. So what is 10 in binary? It's 1010, right? So 1010. Now, so what is CL of log m in this case? It is 4, right? So 4 bits are needed to represent m in binary. So we need, so what is the encoding of 4? It's 100, right? So 100, and this requires 3 bits. So, so I'll represent the number 3 in unary. So I can do this by storing 0001 or 1110. Ultimately, both of them are equivalent. So how did I describe it previously? Yeah, anyway. Okay, so unary would be unary of k would be k zeros followed by a 1. Okay, or k ones followed by a 0, whatever. As long as you're consistent, it's good enough. Okay, so now how does the the decoder actually recover 10, right? So it knows that the first few bits are always in unary, so it will start from the first bit. You keep reading till you get the first one, right? And once you hit the first one, you know that log m is 3. So there are 3 zeros followed by a 1. So it means that the next 3 bits will tell you what log m is. So I read the next 3 bits. I get to know that these 3 bits are 100. So that basically represents the integer 4. So I know that I have to read the next 4 bits in order to recover m. And the next 4 bits are 1010, which represents the number 10. Okay. So let's see another example. Let us say that I have the following. Um, okay. So suppose you are presented with this particular string. Okay. Uh, so now can you tell me how this will work? So what number does this represent? So you first start by reading the first few bits. So what is log m equal to? It's 3, right? So the 3 zeros followed by 1, so it's going to be 3. So I read the next 3 bits. What is this equal to? 5. So the next 5 bits represent, so 5 is basically equal to log m. So I read the next 5 bits. So what does this represent? So what integer does this encode? Right, it's 31. Right. Okay, so let's see maybe one more example. Uh, okay, so can you tell me what integer this represents? Fine, right? So you read the first few bits. You read till you get the first one. So there are two zeros followed by a one. So C log m, this is equal to 2. So I read the next two bits. It is 1 1, which is 3. So C of log m is equal to 3. So these three bits are actually encoding the integer m, and that is equal to 5. Okay. Okay. So now let's see. So this is true in general. So what is the total number of bits that is required to represent this? You need the binary representation. So this requires log m bits. This requires log m bits, and this is encoded using log m zeros followed by a 1. So this is log m plus 1 bits. So the total number of bits that are needed to encode this in binary is log m plus 2 times log m plus 1 bits. Right? Any questions? Okay, so can you tell me when this encoding would be suboptimal or when it would not be good? When is this encoding scheme inefficient, or is it always efficient? Yes? So under what scenarios would this encoding scheme not be good? Sure, when m is large, then sure, more number of bits are required, but that would be required for any scheme, right? So in particular, when do you say that this would improve over fixed length encoding? Under what scenarios is this better than fixed length encoding? Or under what scenarios is it worse than fixed length encoding? Correct. So for if m is always very small, then there's a pretty large overhead because you have to store, in addition to log m, you have to store an addition of log m plus 1 bits. Okay? But even for large integers, uh, can you do any better? Or So this scheme would be advantageous if there is a large variability in the uh, value of m. Right. So if you want to store a sequence of integers, and most of the integers are small, but the maximum value is very large. In that scenario, this prefix-free encoding, this variable length encoding would be advantageous, because most of the time the number is small, but sometimes the number is very large. So if you did fixed length encoding, then you would be wasting a large number of bits. On the other hand, if you know that the number is always very large or always very small, then fixed length encoding is more advantageous than this variable length encoding, right? Okay, so now we've seen sort of two different schemes, LZ78 and LZ77, and now we know exactly how to encode, right? So let us now take an example. Say A, C, D. Let us say that the alphabet is just A, B, C, D. Okay, so that is my alphabet, and let us say that each of these characters are encoded using the fixed length encodings of 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So first, now, what is the parsing of this sequence? Let's take LZ78. Okay. So maybe let me also put some more A, C, B. Just make it a little bit bigger. So the LZ78 parsing would be what? Right. So it's A, AA, AB, AC, D, ACB. Right. And how are these encoded? Okay, so you have 0A, and then what is the next? 1A, and then 1B, and then it is 1C, 0D, and 4B. Okay, great. So now let's look at all the possible integers that we have to encode. We have a 0, we have a bunch of 1s, and then we have a 4, right? So let's see, if let's suppose that we do variable length encoding of the integers. So what is the encoding of integer 0? 0. Uh, why is it okay? 0 1 1 0? Sure. So that is one way of representing it. So the bit 0 is represented by a 0, and then describing this requires one bit, and then one more bit, and then 0 1 represents this in unary. Right? Can we do something slightly better? Can we have a sort of special encoding for bit 0 or for the integer 0? Um, yeah, so this would be a blank for 0. So what would be the encoding of 0, of the integer 0? 1, right? So you can just represent it using the bit 1, and this encodes 0. Right? This is probably easier. It's a slight modification to what I described earlier, but this would be more efficient. So we encode the integer 0 using a single bit 1. Now what is the encoding of 1? Right. So it would be 0 1 1 1. So 1 encodes the integer 1. Then describing this requires one bit, and 1 in unary is 0 1. Okay, great. So what about the integer 4? Right, so it's 1 0 0 1 1 0 0 1. Right. So 0 0 1 followed by three ones, followed by two ones, followed by 1 0 0. Okay, so these are the encodings of the integers 0, 1, and 4. Okay, so now using this, how would we encode the sequence itself? So after all, now we have to encode this in binary, right? So what would the first phrase be represented as? Yes, so 0 comma a. How would you encode this in binary? Right, so it is 1 followed by 0 0, the encoding of a over here. Okay. All right, so now how do you encode 1 comma a? Right. So the encoding of 1 is 0 triple 1, 0 triple 1, and a is 0 0, right? What about 1 comma b? Right, 0 triple 1, 0 1. 1 comma c similarly would be 0 triple 1, 1 0. 0 comma d, what would that be? Be 1 followed by 1 1. And now what is 4 comma b? It would be 0 0 1 1 1 1 0 0 followed by 0, 1. Right? So the sequence AAAAA, BAC, DACB would be encoded using limp-LZIP or LZ78 in this particular form. All right. And how would the decoder work? The decoder starts from the very left. It knows that the first thing that it has to read is an integer. So it reads, so it's 1. It knows that this is encoded by the integer 0. So this is 0, and this represents A. So it goes to the next. So it knows that now it comes to the next phrase. It's 0, 1, which it knows is the integer 1, and 0, 0 is A. Next, 0, 1, this is integer 1, 0, 1 is B. This is 1, this is C. And now it knows that 1 is basically integer 0, and 1, 1 is D, and 0, 0 comma D, and this is the integer 4, and this is B. Right? And since we're using a prefix-free encoding, you know exactly when to stop decoding that particular integer, right? So overall, when you concatenate all of this, you still get a prefix-free encoding of the sequence, right? So LZ78, so the LZ78 algorithm is instantaneous. It is prefix-free, and at the same time, it is universal because we're not feeding it any input distribution. The way you parse the sequence and the way you encode each symbol in the sequence does not depend on any probability distribution. Right? It is just a parsing into different phrases. All right. Any questions? Okay, so here's a question. What's the total number of bits we used to encode this particular sequence? So what is the length of the code word in this particular case? So it's 34 bits. Right? And if I did a fixed length encoding of the sequence instead of doing any compression, okay, just represented each symbol using 2 bits, then how many bits would I need to encode? 22 bits, right? So this begs the question, are we really doing any sort of compression over here? So under what circumstances do you think LZ78 would be would actually give you a good compression? Yes. So for what kind of sequences would LZ78 or LZ77 perform well? Or in other words, why do you think LZ78 is not performing very well for this example?
Maybe n is small.
Sure. So of course n is small. That's definitely true. So for short sequences, the Lempel-Ziv algorithms perform very badly. So even if n is large, it's still, I mean, you could think of scenarios where it could require a large number of bits, right? It may require, of course, it's not necessary. But yes, so Ritvik points it out that the phrases are very small in this case, right? So the LZ78 algorithm or the Lempel-Ziv algorithms would not give good compression if the phrases are small. So if you want good compression, then hopefully the the size of each phrase must be large. So the larger the size of the phrase, the fewer the number of bits that you would require to encode. Right? So 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 really, ultimately, the performance of the Lempel-Ziv algorithms will depend on the number of phrases that the sequence is passed into. Okay, and here is one very interesting property. Now both one can have different proofs of optimality of LZ77 and LZ78 algorithms. In this class, I won't give a complete proof, but I'll still discuss how one can show that LZ78 can indeed be optimal. Okay. So in fact, one can prove very strong results on LZ77 and LZ78 algorithms. They work not just for random sequences, but in fact, given any arbitrary sequence. So note that ultimately Huffman codes or Shannon-Fano codes, arithmetic codes, all of these perform as well as the distribution that is provided to them. Right? If you know the exact distribution, then they perform well. If you don't know the exact distribution, then there is a small loss. Right? And that loss is basically equal to dpq, where q is what you use to is the estimated probability and p is the true probability. Whereas in the Lempel-Ziv algorithms, you're not inputting any sort of probability distribution into the algorithm. It just works without any such information. So, so what is perhaps surprising is the following result. So given any sequence xn, so consider any sequence. I don't even say that this is random. Okay, but the only assumption that I'm going to make is that n is very large. Okay, so consider any long sequence. I define so so for any positive integer k, which is much smaller than n, think of k to be a large enough constant and n is tending to infinity. Okay, that's the way to think about these two integers k and n. So I define the kth order conditional empirical entropy in the following fashion. Okay, so you first estimate, so let's call p hat of ak plus 1 given a1, a2 up to ak. Okay, so this is my the kth order conditional distribution. So it is basically the fraction of times you observe a symbol ak plus 1 after the subsequence a1, a2 up to ak. So for example, if I have a b c a d, okay, then p hat of say b given a, right? So this is the number of, this is the fraction of times the sequence, sorry, the fraction of times b occurs after a. So in this case, there is one occurrence of b after a, and the number of times a occurs is 1, 2, 3, 4, 5. Right? So it's 1 by 5. Similarly, p hat of a given a is the fraction of times a occurs after a. So this occurs 1, 2, 3, 3 times. 5. Sorry, this should be 3 over 4. So it's number of times AB occurs divided by number of times A occurs minus 1. So, sorry, this is the number of times A occurs. So the fraction of number of times A occurs. So it is 1 over 5. So the p hat of A given A is the ratio of the number of times AA occurs divided by the number of times A occurs. And what is that equal to? It's 3 divided by 5. So what is p hat of C given A? So it's the fraction of times AC occurs. So it's the number of times AC occurs divided by the number of times A occurs. What is this? So it's the number of times AC occurs, right? So you never see any AC in this particular sequence. So it is 0 divided by 5. And similarly, p hat of D given A is the number of times AD occurs divided by the number of times A occurs. What is that equal to? It's 1 over 5. Right? So this is a valid conditional distribution. So similarly, this is sort of the first order conditional empirical distribution. Similarly, you can define the first order conditional empirical, the kth order conditional empirical distribution. Right? And using this, we can define the kth order.
Sheriff.
Yep.
Sheriff, there was no D in the end, then the denominator would have been 4, right?
Yes, that's correct. So if there was no, if the sequence ends with an A, then it would be number of times whatever occurs divided by number of times A occurs minus 1.
So then it would be easier to write it as number of times AX occurs, X being any other alpha.
Exactly. Exactly. Yep. That's right. So it's basically number of times AB occurs, number of times AA occurs, and you basically normalize it to make sure that it's a probability distribution. Right? So you take the empirical, the number of times each pair or each k tuple occurs, and then just normalize by normalize to make it a probability distribution. So the kth order conditional entropy is basically exactly as you might imagine. So I'll call it hk of xn. It depends on what the sequence xn is, and it is basically a1 to ak plus 1 summation overall a1 to ak plus 1 in x to the k plus 1 p hat of a1 through ak plus 1. So this is the empirical frequency of observing the subsequence a1, a2, a3 up to ak plus 1 log 1 over p hat of ak plus 1 given a1 through ak. Okay, it's just a standard conditional entropy, the kth order conditional entropy, h of, so this is essentially similar to h of xk plus 1 given x1 through xk, right? But this is defined by a sequence x1 through xn. So it's a natural enough definition. All right. So now we can really say what the performance of LZ78 is going to be. So the claim is that, okay, so fix any k, which is a constant, okay, a constant independent of n, then the length of the LZ78 compression of xn. So for any xn, not necessarily IID, not so absolutely no assumption, no further assumptions on xn, then the length of this is less than or equal to n times hk of xn times 1 plus delta n, where this delta n tends to 0 as n tends to infinity. So this is a remarkable result, and it says that irrespective of what the sequence xn is, as long as n is sufficiently large, and k is some constant which is much less than n, the length of the LZ78 compression of xn is always going to be less than or equal to n times the kth order empirical conditional entropy of xn. All right, and in particular, this also tells us that if the sequence is in fact random, if it is stationary and ergodic, then as n tends to infinity, this converges to the kth order conditional entropy, which is equal to the entropy rate of the stationary and ergodic source. All right, but this statement is true for any sequence xn. And yeah, this is completely lossless. So while decompressing, you will get back the original sequence as it is. But of course, so one point to note is that this this result is good only if n is sufficiently large. So in fact, there have been many different proofs of optimality of LZ78. The textbook by Core and Thomas, it shows that for a random sequence, the length of the LZ78 compressed text converges in probability to roughly n times the kth order empirical entropy. There were other proofs. So the originally what Lempel and Ziv proved in 1978 was that for any fixed sequence, the length of the LZ78 compressor is less than or equal to the best possible, asymptotically it's close to the best possible compression length achieved by any compressor. Not exactly in this particular form. So they didn't really give a measure of how small it could be. All they said was that if you have a compressor achieving an expected length, or if you have a compressor for a sequence xn which achieves a length of L, let's call it Ln, then the length of the LZ78 compression of xn is just Ln into, is less than or equal to Ln into 1 plus delta n. Right? But this particular form is quite insightful, and you can derive this using techniques very similar to what is there in the textbook by Core and Thomas. All right. So a very useful, and in fact this result over here, using similar techniques, you can prove a result which is valid not just for LZ78 compressor, but in fact a very broad class of compressors. So suppose that I have a scheme. So suppose that I have a parsing scheme which which partitions the sequence into phrases such that each phrase is distinct. Okay. Suppose we have a parsing of sen into distinct phrases. So no two phrases are identical. Right? And this property is indeed true for LZ78. You should verify this later on. So as long as we have any scheme which parses the sequence into distinct phrases, let us say into C phrases, then the limit as n tends to infinity, C log C divided by n, this is less than or equal to hk of xn, whatever, limit n tends to infinity of hk of xn for any constant k. All right. And note that C log C is a good measure of the number of bits needed to represent each phrase in LZ78. Right. because after all, you're storing a pointer. So LZ78, if you look at the encoding of LZ78, it is basically, yeah, it's a location of a phrase, it's an index of a phrase followed by a character. This is not too much, but it's really this which takes up most of the space. And since there are C phrases, you only need log C bits to encode a particular phrase, right? A maximum of log C bits to encode a particular phrase. So therefore, the total number of bits to encode a particular, to encode the entire sequence is roughly C log C. And and what this result is saying is that the asymptotic rate is C log C divided by n, which is always going to be less than or equal to the kth order empirical entropy. All right. Any questions?
Sir,
Yes.
sir, in which cases here the length is strictly less than nh, sir?
Okay, so in which case, well, it depends. So for example, this statement is valid for every k, right?
Yes, sir.
Valid for all k, which is a constant independent of n, right? So for example, if you have the sequence all a's, okay, so you have n a's, okay. So in this case, in fact, it turns out that uh, the asymptotic rate is vanishing in n, right? Or even if you have a lot of repetitions, let us say that I have the sequence, all right, so A, B, C, A, B, C, A, B, C, A, B, C, and so on, right? So in this case, H0 of Xn is simply the empirical entropy, and this turns out to be log 3 bits. All right, you can verify this later on. Similarly, you can find H1 of Xn and so on. And it turns out that H1 of Xn is strictly less than H0 of Xn. So, uh, so therefore, and because of this particular reason, the limit of C log C divided by n as n tends to infinity is going to be strictly less than H0 of Xn. Okay. So typically H0 of Xn is less than or equal to H1 of Xn, it is less than or equal to H2 of Xn, and so on. If the sequence is indeed behaves like a kth order Markov source, then this will be strict up to Hk, and then the rest of them will be the same, Hk plus 1, and so on. So if this is a real kth order Markov source. Okay, so we're almost out of time. So let me just hand out the quiz. This is in the chat box. If you're not able to access it, please let me know. Has everyone submitted their quiz solutions? Anyone yet to submit? Okay, so if everyone is done, then I'll stop accepting responses. All right, so yeah, so we'll officially meet next week. If there are any questions, then I can answer them now.